Okay, so here's where we were last time. Okay, time to get started, everybody. Okay, time to get started. So here's hey, everybody, I do need everybody to settle down. We got to get going here. Okay, so last time we were talking about vector fields. Oh, I hit the wrong button. And I made this observation that, very often it's forces that vector fields represent. And in fact, we saw some specific examples of, gravitational fields and electric fields. And this is one of the big uses of vector fields is to represent what I loosely call force fields. Importantly, though, we need to recognize there's another nice, important application, and that is fluid flows. So there's lots of different examples of flowing fluids, and both in 3 dimensions and in 2 dimensions. So in 3 dimensions, again, a bunch of obvious things. How does air flow around the room? That's pretty clear. Ocean currents, if you think about it, right? The water in the ocean is flowing, and at any point in the ocean, you can talk about what the velocity of the water is at that point, et cetera, et cetera. There's one that I think is worthy of discussion in 2 dimensions. That's animal migrations. It doesn't feel like animals are a fluid, but they really kind of are. Here's the complaint that a lot of students make if I say animals are a fluid. They're like, "Are you kidding me? Come on, they're solid, right?" Right? But if you really think about, let's say, water is like the classical example of a fluid, right? Well, it's made up of a bunch of little particles too, isn't it? You know what I mean? So in some sense, the idea that, it's a bunch of individual discrete particles doesn't really affect the observation that water is a fluid. And likewise, if you have a, great big herd of zebras or whatever, right? They all kind of move kind of along in the same direction, at least the ones that are nearby, and maybe they turn over there, they're going in a different direction, but it really behaves a lot like a fluid. And it's a reasonable point of view to view that as being naturally represented by a vector field. So, anyway, something to think about. Okay, so here's the big first question I want to ask. And this is setting up, this is kind of prepping for something that we're going to spend a lot of time with once we get into Chapter 7. But I'm just going to pose this as a natural and reasonable question to ask, and that is as follows. Suppose you have a vector field representing the velocity of a fluid. So we've got some sort of a fluid flow. Perfectly reasonable question to ask. What is the flow rate? So by flow rate, I mean if you've got some cross-sectional area like this parallelogram down here, and if you ask, okay, well, there's a fluid flowing like so, how much volume per unit time of water is passing through that little piece of surface? Right. Now, here's an example where you may have even seen this discussed, and that is if you talk about rivers, right? And there's a couple different ways to describe the flow of water in a river. You can talk about how fast the water is flowing. That's a velocity, right? That would be what the vector field is representing. And the vector field is representing, at any given point, what is the velocity of the water at that location? But another perfectly natural way to talk about the flow of a river is, how many gallons per minute does it spit out? Right, you go to the mouth of the river, there's just loads and loads of water just dumping into the ocean, right? Okay, how many cubic feet per minute or gallons per minute or whatever? Pick your favorite units. Okay, so that's what we want to relate here, and so the idea is, if we have some sort of an area, some sort of a surface here, small flat area. By the way, how it sits in space is going to matter if you think about it, right? So if the fluid is flowing that way, coming at you, right? Then if I orient the area like this, then there's going to be a significant amount of volume of fluid passing through. But if I orient my hand like this, then there's a lot of water passing near the surface on either side, but not very much, if any, going actually through the surface. Right, so the orientation is going to matter. So we're going to represent how that piece of surface is oriented by what we call its unit normal vector. That's this little n right here. Okay. So that's the question, and here's how we're going to get our hands on answering it. First thing I'm going to do is just to set up things. I'm going to talk about this vector called d. We're going to talk about how I might be able to represent d. And keep in mind, we've got the velocity of the fluid that's like this. And so a reasonable question to ask is, okay, well, some little particle of water, if I were to give it delta t seconds, some small amount of time delta t, and ask how far does it move? What is its displacement in delta t seconds? That's what this d is. And so you can see the d vector is parallel to f of x. And f being velocity, d being displacement. What's the relationship? It's pretty straightforward. Displacement is literally just velocity times time. So this d is f delta t. Everybody willing to buy that? It's going to be that edge of the little parallelepiped of water. So in that amount of time delta t, yeah, so this little particle of water makes it up to there, but then all together, all the water that starts passing through at the start of our clock will go in that same direction, and all together we will have a parallelepiped's worth of water. That's the grand total amount of water that passes through that surface in time delta t. I just need to compute the volume of that. And now we actually now have everything we do to be able to do this computation very quickly. So first observation, as I already circled here, volume is height times area. So the area of our little piece of surface, and then times the height perpendicular to that area. That's an old high school geometry formula. Hope you all remember that old high school geometry formula. Height times the area of the base. Hopefully that rings a bell. Let's see here. Now, what is that height? Neat observation to make. If I can find my little button here. Height is literally the normal component of the displacement vector. And again, let's focus on, I'm going to zoom in on this part of the picture. If I can get this thing to zoom. I don't know why here we go. Look at this part of the picture. I drew D over here to get it out of the way, but just as good, it's this purple vector right here. And you can see the height is the component of it in that direction, that being the normal direction. Okay. And then wait a minute, what was D again? Well, we have that conveniently expressed right here. D is F delta T, so let's plug that in. There you go. All right, so let me straighten this back up. Here we go. So all together, all of this having been set up and dealt with, here's our final punchline. The amount of the amount of volume of water that passes through is this. But we're interested in the flow rate. We're interested in volume per unit time. So I'm going to take volume and divide by delta T, and all together then the flow rate dV dt is that right there. F dot N times A. What do you think? Anybody follow? It's ultimately just a bunch of details in a geometry problem, but this this does answer our question. And this expression, F dot N times area, ends up being really important. This is going to be one of the major concepts that we're going to be talking about in Chapter 7. And it turns out this is going to relate to the calculus of vector fields in a really important way. Okay. So anyway, if only because it's the answer to a natural question, but also because it's going to be a major player in later discussions, this deserves a name and a notation. So the word is flux, and the notation is capital Greek letter phi. That's why we're interested in this thing called flux, and this is what flux represents for fluids. How are we doing? Everybody all right? Okay. Now here's a related question. And this one I'm mostly going to leave as an exercise for y'all to think about on your own. It's a nice little exercise. As always, if you get stuck on this, if you're not sure where to get started, if some aspect of it confuses you, whatever, come to my office hours. I'll be happy, very happy to talk with you about it. But this is a really nice little exercise. Let's suppose that instead of velocity, let's suppose that our vector field represents the fluid by way of density times velocity. Seems like an odd construction. Kind of weird. But anyway, let's suppose you do that. The claim then is that instead of the flow rate being flux, instead it will be what you might, I suppose, call flow rate, depends on how you set things up. But instead of volume per unit time, it's quantity, mass, for example, per unit time. That flux computes for you. So you'll notice, again, very similar question. Given some representation of the flow of the fluid, we're measuring some sort of indication of how much fluid per unit time. It's just that here it's in terms of volumes and velocities. Here it's in terms of masses and densities times velocity. So just a little bit different, kind of a tweak. And the way you're going to answer this question, by the way, I'll get you started on it. But again, I think it's a really healthy exercise, and I hope everyone will try this on your own. We need to start off by looking at not volume, but mass per unit time. Right, so we're going to calculate not the volume of fluid in there, but the amount of mass of fluid in there, which just means we're going to have to put in an extra factor of delta. Right? Volume times density gives us that mass that we need. And then that delta carries through. And then at the very end, what you're going to find is that there's this extra factor of delta over here, which thankfully is part of the vector field, right, per our setup. Delta, right here, wrapped up inside of the vector field. So anyway, everything works out very nicely. I've left out the sort of the details on that. So do please fill in those details, think it through. But that's the broad strokes. Okay. All righty. Okay. So this next page, this is one of the few pages I have in my notes that we just don't have time to cover much of. So I'm going to hit some highlights. I want you all to see the very broad strokes, and then I'm going to scratch out a large part of this page as being stuff you're not responsible for. But this stuff at the top, I think, is fine. This is really just an observation that there are some weird fluids out there that don't really behave quite like regular fluids. I've already made this observation when we were talking about, I think it was zebras, that two zebras that are right next to each other, they can't just kind of pass through each other. They can't do that. They bunk into each other, right? So they run together, right? So they kind of have to. But there are some fluids, kinda, that can pass right through other pieces of the same fluid. And my favorite example is light. So now it's tempting to say, look, if you have a light bulb, when you have a light bulb, it's emitting a bunch of photons, right? But two photons that are right next to each other tend to go very similar directions. It feels like they're the same kind of fluid. But if you have two light bulbs, and just for visual convenience, let's make one of them green, and it's shooting out light in every which way, including, at this point over here, there's going to be some photons that are going about like that. And then let's make the other light bulb blue, and it's shooting out photons every which way, including, at this point, it'll have photons going about like that. So now I ask the question, if we were to represent this with a vector field at that point, how do I talk about the velocity of the fluid at this point? I can't. There's two different velocities there. That does not clear what V even means. So this is a non-zebra-like fluid, right? This is really weird. This is not at all like, look, water doesn't do this. Air doesn't do this, right? So it's tempting to kind of throw up your hands and say, well, I guess we can't, there's nothing we can do, no way that we can represent this with a vector field, but that's not so. We just have to get clever about it, and here is the clever idea. We've already established on the previous page that this is the relationship specifically when we're using density times velocity to represent the vector field. This is the relationship between the flow of the fluid and the flow rate, the quantity per unit time. Okay, well, the way we've used this on the previous page is that if you know the velocity, if you know the vector field, and if what you want to know is what's the flow rate, then you can take what's on the right and punch it up, and that will tell you what's on the left. Right? So we've used this as, I know F, what is dm dt? And all we're going to do is turn this around backwards, and I'm going to say, look, dm dt is something that I can empirically measure. Get out there with some actual pieces of surface and just look at the fluid and see what is the flow rate through that little piece of area. That's something that's empirical. And having done that, you can then ask the question of what vector field can I put here that would make this formula work? What vector field would have given me that flow rate? And there's a nasty little question here, which is how do I know that vector field exists? And that's a sticking point. That's just kind of a formality that's not really what this course is about. I claim that that's the case, certainly when we're talking about light, for example. So I claim that can always be done, and this is how you define a vector field representing one of these weird self-intersecting fluids. It's the vector field that makes this equation work. So anyway, I think that's just a neat observation. And sadly now, on to the part that I just have to draw a big X through. And again, it makes me sad because this is a really cool example. If you want to give it a look, I think it'd be healthy. You don't have to. This is not fair game for any exams in this course, so you don't have to know it. But it is, again, it's a good little mathematical weightlifting if you want to give that a try. I think it's a nice one. And again, feel free to come and talk to me about this in office hours. It's really cool. I'd enjoy it. So come on in. We'll discuss. Okay, next part of this discussion on vector fields. Now suppose that back to velocity, representing the fluid flow with the velocity. And let's think about this fluid as being water. Right? So imagine, for example, we're in a swimming pool or something like that, and for whatever reason there's a flow of water in the swimming pool, so maybe somebody stirred the pool or something like that. Right? So there's water kind of moving around in different directions in the pool. If somebody drops a pool floaty, right, into the pool, and imagine that it's perfectly buoyant, right? It's got just exactly the same density as the water, so it's not like it drops to the bottom or floats to the top. It's just kind of perfectly buoyant. It's gonna go wherever the current takes it. That make sense? right? It's not like the pool floaty is going to have a mind of its own and say, look, the water's going this way, but I'm going to go that way. It just can't, right? Okay, so the question is, this pool floaty, when you drop it into the pool, it follows the current, and it's going to generate a path, right? It's going to move along some path, and we can say that, position as a function of time is x of t, and the question is, how do we find this parameterization? Everybody on board with the question? Okay. All right, so how do we get our hands on that? And I'm going to zoom in to this first. And let's talk through the English right here. I think this is a really easy way to think about how we would model this situation, because all this says, pretty innocent observation, is that you want to know what's the velocity of the particle. We got this floaty, and what's the velocity of the pool floaty? Well, it's whatever the velocity of the fluid is. Again, the floaty does not have a mind of its own or any sort of ability to move itself, right? So the velocity of the particle has to be the velocity of the fluid. That's most of it right there. Is everybody on board with that? All right, now we have to recognize, well, yeah, but, look, the pool's a big place, and over on this side, the water's going that way, but way over on that side, maybe the water's going a different way. So the velocity of the fluid is different in different places. So which velocity of the fluid? So I think this is a perfectly reasonable observation. It's the velocity of the fluid wherever the particle is. Right? Around where the particle is, that's the fluid that's actually pushing our particle. So the velocity of the particle is the velocity of the fluid at the point where the particle is currently sitting. And if you then just kind of translate that into math, velocity of the particle, derivative of the parametric curve, the velocity of the fluid, we've previously represented by v. I'm going to stick with that. So v is the velocity of the fluid. We're evaluating that velocity at x of t because that's where the particle is. Everybody on board? All right. Okay. All right, so this pretty much does it for us. There's one last little observation to make, and that is the velocity. I missed. Okay, let me try that again. Velocity is what the vector field is. How we doing? Okay. All right, so altogether we have ourselves what's called a system of differential equations. So given a vector field, right, we have an equation here that involves the coordinates of position and relates them to the derivatives of the coordinates of position. So this is a differential equation. It's actually, again, what we call a system of differential equations because, of course, position has several coordinates. So there's an x coordinate, a y coordinate, and a z coordinate. So there's 3 coordinates here, and likewise 3 coordinates here, and altogether we have 3 equations. So 3 separate, but linked differential equations to solve. And then the big question comes up, how do you solve a system of differential equations? And that's not our job. That's for Math 353. Y'all will see how to do that in Math 353. Those of you who are engineers, those of you who decide to take it. So that's not what we're going to do at all. But we can confirm a solution. Right? We don't have to show how to actually find it. I'm going to give you a solution and show how to check and confirm that it actually works. So here we go. Let's start with this vector field right here. Y'all will recall this vector field from last time. Right? Hopefully y'all recognize this one. This one's the one that ended up being the fluid that's kind of rotating sort of counterclockwise right around the origin in 2 dimensions. You can flip back in the notes to remind yourself how that worked. And claim this is a flow line. Now, how do I confirm that that's true? Well, again, we just have to check that this works in the differential equation. So this vector field allows me to write down exactly what this differential equation is. And if I want to check that something is a solution to a differential equation, well, I just take the thing and I plug it in wherever the x goes. Right? So according to what this says, I'm going to take my proposed flow line, I'm going to take its derivative to give me the left side of the equation. I'm going to plug it into this formula for the vector field to get the right side of the equation. And the claim is that the equation works. That makes sense to everybody? All right. Okay. Good deal. Let's see here. Did I? Okay, yeah, here we go. Okay. All right. So, last thing we're going to say in this section, this is just an observation, and I've been teaching multivariable calculus for many years now, and a classical blunder that I see certain students make is to think to themselves that, oh, you know, I get that we can represent forces like gravity and electromagnetism, stuff like that, with vector fields, and we can represent fluid flows with vector fields, but between these two, a lot of students find that they prefer one over the other. And which one they prefer varies by student, right? But there's a lot of students that decide, you know what, in this class, I'm just going to think about all vector fields from the point of view of, again, one or the other of these. And I just want to point out, you really can't do that. That's not a winning strategy in this course. When we get to chapters 6 and 7, there are some things that we're going to do that require, there's just no way around it. You have to be able to think of the vector field as representing forces. The applications are very specific to that. And also, there are other things that we're going to do with vector fields in chapters 6 and 7 that just, again, unavoidably require that you think about them in terms of fluid flows. So please do not pick between these metaphors. You might think of them as metaphors for vector fields. This is not an either-or thing. This is a both forces and fluids. And you've got to be able to think in both of those terms comfortably. So please do take whatever time you need to kind of get accustomed to both of these examples. Okay. All righty. Moving along. So, 3.4. This is a weird section. This is arguably out of place. Arguably this should, there's a case to be made that this shouldn't really come up until chapter 6. So why is it coming up here in chapter 3? There's, I think, a pretty good reason for this. When we get into chapter 6 and 7, y'all are going to notice, fear not, you will 100% notice there's a lot going on in chapter 6 and 7. It's a lot to digest. It's a lot to get used to. It's very challenging. It's very substantial. There's just a lot going on, right? And so pedagogically, it makes sense to take some of the pictures, some of the images that you're going to be trying to kind of get accustomed to, and just let's just start chewing on those now, right? Get used to those ideas now. So this is a preliminary glimpse, you might say, as to what we're going to do in chapters 6 and 7. Tip of the iceberg only, of course. But these are good ideas to kind of start chewing on and trying to digest, to some extent. Okay. All right. So here we go. We'll start off reminding you of the gradient. I'll remember the gradient. Here's a different way to write the gradient. It's just a different way to write down ultimately the same thing. Now this, what I have on the right side here, is arguably a little disturbing for a couple of reasons. Well, the main reason being this thing that I have written as a vector, partial x, partial y, partial z. Notice inside the parentheses here, partial x is not being applied to anything. So this is not a partial derivative. This is the promise that I will eventually apply this to take the partial derivative of something at some unknown time in the future, right? But that itself is not a partial derivative, right? So it's weird to think about what I have in the parentheses here as being a thing, right? I'm drawing it like it's a vector. It's not really a vector because these elements or coordinates are not numbers, right? Okay. Well, we've seen this before, right? When we defined cross product, right? For example, we talked about this symbolic determinant that, didn't play by the rules. It didn't really quite make sense. It was a weird construct. Somebody made that up, and it doesn't really quite make sense as it is, and yet it's awfully convenient. And if you just kind of accept that, we know it's nonsense, but play along, and it turns out to be super convenient, and it's a very convenient tool. Same thing here. We're going to imagine this thing, just the operator, not operator applied to f, but just the operator by itself as being symbolically anyway kind of its own little thing. And I saw a hand over there.
Does it matter if it's on the left side or right side?
It does. Yeah. At this stage, in a course like this, it only matters because of what I know is coming in future classes, and it will matter then. So at this point, it only matters because it's a very firm, steady convention that you always write the derivative on the left. Otherwise, it really means something different. Yeah. Does that make sense? Okay. Yeah.
I don't understand what it represents if we don't take the derivative of x, for example, of f. What is d over dx?
Yeah, right. No, exactly. No, good. You shouldn't be comfortable with it. Okay, so it is. Let's see how to say this. D by dx by itself. If I look. And my stylus is gone now. Okay, switching. Okay, so if you look at d by dx by itself, it's not a number, not really a function, right? But that represents an action of something that you could do. That's something you could do to a function, right? So think of it as a process, right? And so it's a thing that you can do to something, and so even though it's not a real number, it is a mathematical object in that sense. Yeah, and so again, weird, right? But nevertheless, worth talking about as it's going to turn out. Okay, so this thing, the operator alone by itself is called del. It's not called gradient. Gradient is what you get when you apply it to a function. This is called the del operator, and it turns out we're going to do many things with del other than gradient, in addition to gradient. Okay. All right, so that's just a notation. First example I'm going to show you is something called divergence. Divergence of a vector field is computed by this formula. Given a vector field, we compute it with that formula right there. And now let me talk about the notation on the left. I've written it as del dot f. That seems super weird. Let me come back up here real quick. Remind you that del is that. And notice all I've got here is there's del. Right, it's those partials. And f is those coordinates. And it's as if I'm taking a dot product. Now, again, it's not really a dot product. It can't be really a dot product because that's not really a vector. Right? Vectors have elements that are numbers. This isn't that. As we've already agreed, that's, it's kind of nonsense, but it's a convenient little bit of nonsense. So likewise, this isn't exactly a dot product, but I mean, what would you imagine it would mean to do this dot product? Well, I'd take the first element of the del and then the first coordinate of f, and I can't multiply this times that, but I can apply this to that. And that gives me this first term, and then you add likewise for the other terms. So I'm going to call this a reasonable interpretation of that. Or said differently, this notation on the left is a reasonable shorthand. I'm somewhat reasonably motivated representing this formula. Y'all willing to buy it? Again, with all my disclaimers, this is sloppy and a little bit bogus, but very handy. Now, just so you know, this is not me making stuff up, right? This is not me trying to push the mathematical community into either a notation I like or a notation I don't like. This is extremely standard. This is all over the place. In fact, in my undergraduate days, taking loads and loads of physics classes, I saw this, I would say, most of the time. When I saw divergence, it was written as del dot. That's just the most common way to write it, certainly in my old physics classes. So I predict y'all are going to see that notation a lot. Okay, so that's this is our first little bit of calculus of vector fields, and what does this represent geometrically? Here's where I have to apologize. I don't have the tools that I need to be able to make sense out of what I'm about to tell you. And that really bugs me. I mean, after all, I've gotten up on my soapbox and expounded at length on how, look, it's really important. It's all about the reasoning. You can't just make baseless assertions. You got to explain why. This course is all about why. It's all about reasoning. And now I'm going to violate that rule, right? So there's no way around this. I just can't give you the why yet. That will come to the extent we can in this course. That will come in chapter 7. So until then, I'm just going to claim and hope you're willing to believe me that divergence, aka del dot f, it represents the amount that the fluid is flowing away from the vicinity of where you've evaluated your divergence. That's just a claim. I'm going to show you some examples in a moment here of what we mean by how much the fluid is flowing away, but this is the claim. So let's see the example. Here's our classic first example. Y'all will probably recall we've already studied a vector field that looked very, very much like that. This is three-dimensional, though, instead of two-dimensional. But by a similar argument, I claim this is what it looks like. Make sure you can do this. So think back to, again, we've previously written down f of x comma y equals x comma y. This is the same thing, but three-dimensional. The field vector is the position vector for the input point. So it looks kind of like that. Okay, so let's compute the divergence. And yada, 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 compute. And it turns out to be 3 in particular positive. And so keeping in mind that divergence represents how much the fluid is flowing away, the fact that we got a positive amount suggests that here, and by the way, notice I'm evaluating this at the origin, suggests that this vector field represents the flow of a fluid away from the vicinity of the origin. And I think that comes through pretty clearly in the picture. Everybody see what I'm talking about? The fluid's flowing away from the origin, just like divergence said it should. All right. Okay, so this is the classic first example. And now there's a lot of other stuff to say about divergence, and we'll see a bazillion examples again when we get to chapter 7. What I want to talk about here is how you think of this physically. because there's actually a really confusing potential here. The following confused me for a very long time. This was when I finally figured it out. I was like, why didn't anybody tell me that? Oh my gosh, it could have saved me so much frustration. So I'm going to tell you all now, early. When you think of this as being a fluid, there's actually a couple of different scenarios, kind of types of fluids that it might actually be representing. And they give very different punchline physical interpretation. So here are my two examples. Let's suppose that what you have here is the top of a tall tree. And in my mind, let's think palm tree. So, you've got there you go, tall palm tree, right? And maybe there's a bunch of birds up here on the fronds, and they're taking a rest or whatever, and then something happens, car backfires, and they all get scared and they all fly off. Well, that's what this would look like, right? You could think of the birds as being a kind of a very coarse kind of a fluid of sorts. And as the birds fly away, the interpretation, sort of the punchline that you might imagine as these birds fly away every which way, is that, well, there were a bunch of birds, but then they started flying away, and as they start flying away, the number of birds is decreasing. Right? There's a certain amount of birds in the tree, and as they start to fly away, now there's less and less birds in the tree. Right? Reasonable punchline? So that was the only picture I had in my mind for a long time when I was first learning about this kind of stuff. And then I encountered other scenarios, and again got super confused for a long time. So here's the other scenario, though. Let's imagine that instead of this being a bunch of birds, let's imagine that's a light bulb. Now, light is a fluid, right? Again, of sorts, right? A bunch of photons flying around, just like they're little particles of light instead of little particles of water. Right? Well, you could imagine that a light bulb would generate a flow kind of like this also. Maybe, again, might have a positive divergence. You would expect it to have a positive divergence after all. Does this mean that you're losing photons? Light bulbs don't have photons stored in them. It's not like there's a photon reservoir, right, in light bulbs. If you take an inert light bulb that's not flipped on, there are no photons in it. It's photon empty. The light bulb generates the fluid. Right? So in this case, if we're talking about, again, the flow of light out of a light bulb, there's no decreasing density. Why did I hit that button? There's no decreasing density. Rather, what's going on, what this divergence represents, that represents the extent to which light is being created by the light bulb. And again, you could imagine that, like, again, if you've got photons flying out of this light bulb, yeah, that's because it's generating those photons. So you get a totally different sort of physical conclusion because it's a totally different kind of a fluid. All right, yes?
So when we're talking about fluids, do you differentiate between particles and waves?
I know what you mean. Yeah, I'm assuming that I'm taking the particle point of view on light here, and yes, there's a whole wave-particle duality and complicated physics conversation ensues. But no, this is not a quantum mechanics. Let's just think in terms of particles, and I don't want to get any nitty-grittier than that. Yeah, is that okay?
Yeah.
Yeah. Good concern, though. Good concern. Okay, just one more complication. It turns out there are some fluids. Come talk to me in office hours if you want to hear more about the following. But there are some fluids where both of these apply simultaneously. And that's weird. And then how does divergence relate to that? That's a whole conversation. Okay. All right. Okay. So anyway, I just wanted y'all to be aware of these sort of two extremes, and don't just assume because this makes sense that this must apply to all fluids. Some fluids are like this. Some fluids are like that. Okay. Another example. So vector field, that's what it looks like. Make sure you can do that. It's a matter of thinking it through, right? Plot some points, whatever you like. But anyway, there you go. You can compute the divergence, and the divergence ends up being 0. And notice, this is 0 at any point A you might happen to pick. So, for example, right there, if I were to look in this vicinity here, that orange vicinity, it says the divergence is 0. Does this mean that there is no fluid flowing away from that point? It looks like there is. I see fluid flowing away from the point right there. What gives? So what gives is that there's also fluid flowing into. And so one important thing to keep in mind about divergence, it is the net outward fluid flow away from a vicinity, right? So there is a positive outward flow here. The inward you can think of as being a negative outward flow. And so the negative and the positive effectively cancel here, or said differently, the fact that the divergence is 0 is telling us that the negative and the positive cancel there. Okay. So just another thing to keep in mind. All right. Next thing to define, again, we'll have to be quick about this. I'm going to define this thing called curl. It's a weird formula. It's another one of this symbolic nonsense kinds of things. So this is like doubly symbolic nonsense, because on the one hand, I'm going to define the cross product with the symbolic nonsense of this matrix, air quotes, right, matrix determinant. But then also, there's the further symbolic nonsense that the del operator, again, treating it as if that's a vector, right? So again, double nonsense. But if you follow the symbolic nonsense rules of cross products and compute as if this is okay, right, in the usual way, and interpret it in the only ways it could possibly make sense, and you write this down, what you will get is, in fact, exactly the definition of this thing called curl. Okay, so again, weird formula. Not at all clear why we're doing any of this other than it's going to come up later, right? But I've given you no motivation for why this formula, why are we writing down this formula? So again, I have to apologize. I'm just going to make an assertion here with no motivation. Gives me the willies to do this, but anyway, here it is. What curl represents, in some sense, is how much and around what axis we have a kind of I'm going to call it a rotation of the fluid. So you think back to our stirred pot, right? We had this vector field representing a flow of fluid around somebody getting stirred the pot. You got this motion here, right? So that's going around an axis. Right? And you could imagine sometimes maybe the pot wasn't stirred very much and it's sort of rotating slowly, or you could imagine somebody went crazy, right, made a little whirlpool and it's rotating fast. So more rotation will give you a greater magnitude of the curl. Less will have less magnitude, and the axis of the curl, the direction of the curl is always the axis that you're sort of rotating around. Again, y comes much later. Classic first example, vector field, picture. Now this is a three-dimensional version of the stirred pot. Good exercise to think through, right? Make sure to persuade yourself that This is kind of a slice, if you will, of what that vector field would look like. It's just sort of a three-dimensional stirred pot. And you can compute the curl. Compute. Out comes 0, 2, like so. And as it's supposed to, notice that the curl is pointing in the direction of the axis that the water is rotating around. Is that cool? Again, this is an example of an assertion. I'm not giving you reasoning. I'm just giving you an example of an assertion, and the reasoning is going to come in chapter 7. Okay, we'll see y'all later. Have a good rest. Have a good weekend.